Hello everyone and welcome to this lecture on N-gram language models. In this lecture we will explore the fundamentals of language modeling, focusing on N-gram models and their applications in natural language processing. We will also discuss their significance, how they are built, evaluated and improved through smoothing techniques. So language models are essential tools in natural language processing. They help us estimate the probability of a given sequence of words. So unlike formal grammars, which classify sentences as strictly valid or invalid, probabilistic language models assign probabilities, making them useful for practical NLP tasks. So, for example, consider some sentences in English are grammatically correct but rarely used, while others are ungrammatical yet commonly spoken. A probabilistic language model helps us determine how likely a sequence of words is, which is critical for various applications. So some uses of language models. As you probably know, language models are foundational in many applications, including, for example, speech recognition. So given an audio input, the model identifies the most likely sentence. If someone says something that sounds like the example here, I ate a cherry, the model will likely predict I ate a cherry as the correct phrase. Another application is optical character recognition. When scanning documents, error can occur in letter recognition. A language model can ensure that words make contextual sense within the document. Machine translation. Translating languages requires choosing the most probable phrase from multiple possible translations. Text generation, like chat bots and AI-generated content, rely on language model to generate natural-sounding text. And spelling corrections as well. So instead of using just a check for known words, language model look at context. For example, if someone says there are problems with this sentence, then the language model can identify where the errors are. These applications demonstrate how probabilistic models enhance real-world NLP systems. So another key application of language model is predictive text input. You've likely encountered this while typing on your phone or using a search engine. Based on what you've typed so far, the model predicts what word is most likely to come next. For example, please turn off your cell. The highest probability word here will probably be phone, or your program does not. The most likely word to complete the sentence is work. So these models are trained on vast amounts of data and text and learn patterns to assist users in typing more efficiently. Now let's look at N-gram models. So an N-gram model estimates the probability of a word based on the preceding N-1 word. This helps approximate sentence probability efficiently without requiring infinite data storage. For example, in a unigram, we only consider the probability of a single word. The probability that the word is phone, for example. So if I want to complete the sentence, please turn off your cell. If I use an n-gram, a unigram, then in that case, I'm just calculating the probability of the word phone. Now, if I use a bigram, then I'm going to say, what's the probability that the next word is phone, given that the preceding word is cell? So the n-1 word is cell. A trigram would use the two previous words. So what's the probability that the next word is phone, given that the two previous words were yourself? So these models assume that the only most recent words matter for predicting the next word. This assumption is called the Markov property, which simplifies computation but sometimes limit accuracy. As you can guess, when we have a long sentence, towards the end of the sentence, for example, verbs, for example, will depend on who the subject is, and the subject maybe was stated very early in the sentence. So that can lead to some errors if you're using an n-gram that doesn't capture this context or word dependency. So we'll look more at this later in the lecture. So to compute the probability of a sentence, we use the chain rule of probability. Essentially, we expand a probability using conditional probability. So what's the probability of word 1? And then multiply that by the probability of word 2 given word 1, and then word 3 given word 2 and word 1, which is itself can be expressed as probability of word 3 given word 1 squared, and so on. This is the chain rule all the way up to n words. If you're using bigrams, then in that case, you're only calculating the conditional probability of a word given the previous word, so the probability of word k given word k minus 1, and then you multiply these probabilities across all the words in your sentence. That will give you the probability of a given sentence. The n-gram approximation, in that case, probability of word k given all the words from n minus 1, from k minus 1, sorry, to n minus 1. So we estimate the n-gram probabilities using relative frequency count. So essentially, we look at our large test, the training text we have, and we see the frequencies that each word happened in the text. And that's how we're going to estimate these probabilities in bigram and n-grams. So to maintain a structured probability space, we start with a special token. So in that case, for example, the S, and we end the sentence with another token, which is a slash S. We compute word probabilities using the observed frequency in our training data. How many times the word happened relative to the total number of words in our dictionary. And then we assume missing combinations have a probability close to 0, which can be adjusted using smoothing techniques. So we'll talk more about words that we haven't seen in the dictionary in the training, but appeared in the test set later. Now, an n-gram model, like we said, is a probabilistic generator that can construct sentences by picking words based on learned probabilities. The model is trained using maximum likelihood estimates, which chooses parameters that maximize the probability of the training data. So the process is, number one, first step is initialize the sentence with a start token, predict the next word using the conditional probability, and then repeat until you reach the end token of the sentence. This technique is used in AI text generation like chatbots and autocomplete systems. Now, how do we handle unknown words? So it's possible that we can. Here's an example before we move on. So the probability of the sentence "I want English food" is essentially the probability of the word "I" given the start of sentence, that we're starting a sentence with "I", which is 0.25, times the probability of "want" coming after "I", which is 0.33. That's again based on this combination in the training set, times probability of English given the word "want", 0.0011, times the probability of food given English, and then finally the probability that we reach the end of sentence given that the last word was food is 0.68. You see that the two sentences, one of them has a probability of 0.00031 and the other one has a much higher probability, 0.0019. So that's how we calculate the probability of a given sentence. So, like we said, a language model must be trained on a large corpus of text to estimate good parameter values. Models can then be evaluated based on their ability to predict high probability for disjoint test corpus. So we keep out a set of the data for testing purposes and see what probability each combination of words gets. Ideally, the training and test corpus should be representative of the actual application data. So it is possible that you start with a generally trained model, and then you do what's called transfer learning, and then do some in-domain data training by adding highly weighted small corpus to the original training data that was used to generate the original model. Now, a major challenge in n-gram modeling is handling out of vocabulary words. So some strategies to address this include using a special token to represent rare or unseen words. So the model is allowed to say the probability that the next word is unknown given that the last word is food, for example. Or limiting the vocabulary to frequently used words and replacing the rest with that unknown token. That also is a possibility. Or assigning probability to allow generalization to new words. Now, these methods helps improve model robustness in real-world scenarios. Language models are evaluated using a metric called perplexity. So essentially, there are two ways to evaluate them. One way is to evaluate them in a real-world application, which is realistic but expensive. And the other way is like we do with any other machine learning model, which is to use a separate test corpus, which is less realistic but cheaper. So typically, you would verify at least once using a test corpus, and then before you go to real life testing. So the metric used to evaluate a language model is called perplexity, and essentially it measures how well a model fits the test data. So I use the probabilities that the model assigns to the test corpus. So normalizes for the number of words in the test corpus. So perplexity of a given word W is the nth root of 1 over the probability of the specific word that was assigned by the model. So, for example, if this model was trained on 38 million words from the Wall Street Journal using a vocabulary of close to 2,000 words, and we evaluate on a disjoint set, so unseen set of 1.5 million words from the same Wall Street Journal. So you can see that the perplexity goes down as the model complexity goes up, which is expected. Now, smoothing techniques, we don't really address that in this class, but since many word sequences never appear in training data, basic models assign them a probability of 0, leading to infinite perplexity. So you can see here, if the word combination W1, W2 all the way to Wn never happened in the training set, the probability of this combination will be 0, which will give you perplexity of infinity. So to deal with this problem, we use smoothing techniques. So one technique, for example, is called Laplace add 1 smoothing, which adds 1 count to every possible word sequence. Another one is good Turing discounting, which adjusts the frequency based on unseen word patterns. Other methods refine the probability assignment based on word diversity. So these techniques ensure that unseen events get reasonable probability, making models more reliable. We just want to make sure that we never get a division by 0 when we calculate the perplexity. So to conclude, n-gram language models, they assign probabilities to word sequences. They help with speech recognition, machine translation, text prediction, require smoothing to handle data sparsity, and evaluated using perplexity and real-world performance testing. So although simple n-grams are useful, advanced techniques like deep learning models, like transformers, which you probably heard of, with large language models, have surpassed them in performance.